Hello everyone, I'm Nolan Walberger and thanks for joining me. We are on an adventure looking at the Casteljau Bezier curves and relations with algebraic calculus. Today I want to reinforce our new understanding of affine points and vectors and how to work with them algebraically by looking at the Casteljau Bezier curve of degree 4, the quartic case, and examining what I'm going to call the midpoint hierarchy or midpoint structure of this curve. And then we'll look at dynamics, discrete kind of dynamics on the actual Casteljau Bezier polygon that determines the curve. So we're making a bridge here between sort of continuous calculus and discrete calculus. In the algebraic calculus course, the discrete calculus is very prominently studied, and that's one of the points of, I think, interest. It's usually not covered in a calculus course, but for us, understanding differences and difference operation and summation in the discrete case is very important, and it'll turn out that the Casteljau Bezier situation is intimately connected with that in a very interesting and lovely way. So let's start by looking at our quartic Casteljau Bezier curve with control points P0, P1, P2, P3, and P4. So we have 5 control points. And it's algebraically given by the locus of this expression here. Okay, so there's a point T0 determined by the 5 control points. And then we have this expression involving combination of P0, P1, P2, P3, and P4. And here you see the degree 4 Bernstein polynomials, which have the coefficients 1, 4, 6, 4, 1, the binomial coefficients associated with 4, and also these powers of 1 minus t and t. Okay, and then we can rewrite this in terms of increasing powers of t squared, t cubed, etc. And we get these expressions. Well, we get the binomial coefficients again, but then we also get these expressions in the control points. And we know now that we can interpret these as vectors because the sum of the coefficients is 0 for this one here, this one here, this one here, and this one here. Not the first one. The first one is a point, right? So we have a point plus a vector plus a vector plus a vector plus a vector with the multiples depending on t. Okay, so we see here both affine combinations of points in that first line and a combination of points and vectors in the second line. And we're particularly interested in the nature of these objects that appear, which are actually vectors. What do these vectors mean? Where are they on the diagram? We're going to be looking at that, and later on in the next video when we talk about the discrete calculus, you'll see these are very important kinds of objects going back to Harriot, going back to Gregory and Newton in some sense. So we're going to be touching base with some really classical calculus here. Okay, so let's have a look at this thing. Scroll down here a little bit so you can get a picture of this thing. Okay, there is a quartic. Okay, and here what we're looking at, okay, is we're considering a sort of a snapshot where our parameter t is just at 0.5, okay? So that's a pretty important special case. We've seen that in the quadratic and cubic case, that particular value has an important role when we're interested in integrating or finding the signed area of the corresponding curve. Okay. Now, we don't know whether there's a corresponding formula for quartics. That's a big open question for us. But it seems clear that at least there's some sort of geometrical interest in this intermediate value halfway between 0 and 1. And we're going to call this thing sort of the midpoint hierarchy of the Casteljau Bezier curve. All right, so since we haven't had too much experience with the quartic situation, let's have a look at it. Let's play around with GeoGebra here. Okay, so here's our polygon, P0, P1, P2, P3, P4, 5 control points. Here's Q0, Q1, Q2, Q3. Then the next level, R0, R1, R2. The next level, S0, S1, and finally T0. Now this is T equals 0.5, which we're particularly interested in, but of course we can vary this. And as we vary it, we go around the curve in a pleasant way. Whoa. I'm allowing values less than 0 and greater than 1 here also, so we're going beyond just this portion of the curve. Now, it's kind of fun to drag this around, because that's why we like things like GeoGebra. So let's drag some of these control points around and see what happens to the Casteljau Bezier quartic curve as we do that. Okay, now let's just move around and see what kind of things we can come up with. All right, just to give you a sense of what a quartic curve looks like. Actually, we were quite happy to move our points around quite arbitrarily, right? We don't have to have a convex polygon. These control points can be pretty well anywhere. And this is the beauty of it. The same story is still happening. We still have Q0 and Q1, Q2, and so on. And and everything is really just as before algebraically, but it's quite a rich kind of structure. Okay, let's go back to some intermediate value between 0 and 1. Well, where are we? 0.2, 0.4. Okay, fine. Okay, let's move these around a little bit more just to get a sense of a quartic curve. Oh, there's a kind of interesting little loop there. Yeah, okay. All right, see, we can even cross it like this. Well, you see, so there's kind of a double, and there's a loop here, and there's a kind of a loop here, right? Oh, there's almost like a figure 8. Okay, these are lovely objects, right? These are great. It's really interesting for us to try to study these things. Okay, so let's go back to our sort of more standard picture where we can sort of see things pretty clearly. And we're especially interested in this particular value, t equals 0.5 or 1/2. Okay, so then we can give explicit expressions for all of these points, and I think it's interesting to do that. All right, so let's just quickly go through it. It's completely elementary, but instructive perhaps. So starting with the Q's, all right, so Q0 will be the midpoint of P0 and P1, and we know how to do that affinely. It's 1/2 P0 plus 1/2 P1. That's an affine combination of P0 and P1, which is giving equal weighting to the 2 points. So that's the midpoint. That's how we describe the midpoint of the segment P0, P1. And correspondingly, Q1 is the midpoint of P1, P2. Q2 is the midpoint of P2, P3. And Q3 is the midpoint of P3 and P4. Excellent. Okay, so now we go to the R's, okay? And of course, you know what the story is. R0 is the midpoint of Q0 and Q1, and R1 is the midpoint here, and R2 is the midpoint there, okay? But we want formulas for these things now, okay? So we can take the formulas that we have for the Q's, and we can then quickly find formulas for the R's. So R0 will be the midpoint of Q0 and Q1, and we just plug things in and just do everything algebraically. So it's 1/2 of this expression plus 1/2 of this expression. And you just work out what that is. That's 1/4 P0 plus 1/2 P1, because you're getting a quarter from this term and a quarter from this term, plus 1/4 of P2. So then correspondingly, R1 is just what you get when you jack up the indices, and R2 what you get when you jack up the indices again. Right, so those are the expressions R0, R1, R2 in terms of the control points. And notice that if we pulled out a factor of 1/4 here, the coefficients are really in the ratio 1 to 2 to 1. Over here, they're in the ratio 1 to 1. Here is 1 to 2 to 1. Okay, next level, the S's. The S's are midpoints of the R's. So S0 is 1/2 R0 plus 1/2 R1. So we have to take 1/2 of this quantity here. That's R0 and 1/2 of R1. There it is there. And we just figure out what that is. Okay, and it's this expression now involving P0, P1, P2, P3 with weights 1, 3, 3, 1. But we have to divide by 8 because the total sum of the coefficients has to be 1 to get an affine point. And S1 is corresponding to the same thing. You just jack up the coefficients, the indices, and you going from P1 to P4. And finally, so the top level for the quartic, the T0 is 1/2 of S0 plus S1. So we just take the average essentially of this expression and this expression, and you work that out, and you get 1/16 P0 plus 1/4 P1 plus 3/8 P2 plus 1/4 P3 plus 1/16 P4. And the coefficients here, although we've lost the common denominator, but the coefficients are really 1, 4, 6, 4, 1 with a common denominator of 16. Now, you might be tempted to sort of rewrite this, therefore, in this form. Have a look at this. Is this correct? Okay, I mean, algebraically, it's correct. It's the same. Okay, we just pulled out a factor of 1/16. And now we can more clearly see the binomial coefficients corresponding to 4 arranged there. But I want you to appreciate that this is technically not well defined for us, okay? Because we are not able to make sense of the expression P0 plus 4P1 plus 6P2 plus 4P3 plus P4. What's inside the brackets here is not defined. Okay, we do not have an arithmetic of affine points in general. We only have an arithmetic of affine points when the sum of the coefficients is 1. Okay, so this thing here makes sense. This is a completely legitimate point. This thing is really questionable. In fact, strictly speaking, does not fit inside our world. Okay, great. Okay, so here's the picture again. So we can maybe now draw some conclusions, and it might be interesting to do that. Okay, so here's just a simple example of that kind of thing that you could maybe extract some information. Okay, so the claim here is that S0 to S1, this line here determined by the S points, is parallel to R0, R2. Okay, but not in general to Q1, Q2. There's Q1, Q2. Or to Q0, Q3. At the face of it, you might say this looks like pretty close to being parallel, but actually the S0, S1, which is the tangent to this midpoint when t is equal to 0.5, it's only parallel to R0, R2. And how could you, algebraically just convince yourself of that? Well, compute the vector. Okay, now we're talking about vectors, relationship between points. So the vector from S0 to S1, remember, we want to express that now as a difference. Okay, so we write that as S1 minus S0. So here was our expression for S1. Here's our expression for S0. So we're going to take the difference of those two things. Here the sum of the coefficients is 1. Here the sum of the coefficients is 1. When we take the difference, we're going to get sum of coefficients equals 0, which is the criterion for being a vector. Okay, what do we actually get here when we do this? Let us expand this. Okay, so we get, maybe I'll rearrange this so it's in order of increasing labels, which is what I've been doing before. Okay, so what is this? It's minus 1/8 P0 minus 1/4 P1 plus 1/4 P3 plus 1/8 P4. And the sum of the coefficients is 0. So this is expressing a vector, which is what we'd expect because it's the difference between 2 points. Now, how about the vector from R0 to R2? So that's down here, okay? R2 minus R0, so there's the expression for R2. There's the expression for R0, okay, separated by 2 in terms of the indices. If we evaluate this, and let me, again, put it in more standard form with our P0 at first, and then P1, and then P3, okay? So now we can compare this, okay? What's the relationship between this one and this one? There's a quarter, half, half, a quarter, 1/8, 1/4, 1/4. So this looks like this is equal to 2 times what we just calculated, which was S1 minus S0. Okay, so indeed, so we've just determined that this vector is half of this vector, which is not at all a surprise because we basically sort of have similar triangles here, but we've just done it algebraically without even having to register or anything on the geometry side. We're just doing it algebraically. We just have control of all the points so we can create the vectors, and everything is nice. So indeed, we can conclude that S sub 0, S sub 1 is parallel to r sub 0, r sub 2. And I'll leave you to calculate expressions for vector between q1 and q2, say, or between q0 and q3, and convince yourself that those vectors are not multiples of s1 minus s0. Great. Okay, so now I'm going to tell you about velocity and acceleration. So let's talk a little bit about velocity and acceleration and higher such things. So we all know that if we have some trajectory of a particle, then physicists are interested in the velocity at a point. So we have a point on some kind of trajectory, and we're interested in the velocity at that point. Or maybe we're interested in the acceleration at that point. Now, those are differential calculus notions, typically, traditionally, involving derivatives, okay, which are traditionally done with limiting procedures. In the algebraic calculus, we have another way of thinking about that. But, okay, from a naive physical point of view, we can think about that. You have some very small little segment of the curve, and you compute a change in position divided by a change in time, and you get a sort of an approximate velocity, and then you look at the limit as this little thing gets closer to a point. Okay, so that's sometimes called an instantaneous velocity. Now, over in the discrete world, okay, where we just have discrete time intervals, particles here at time 0, here at time 1, here at time 2, here at time 3, etc. Okay, we can also talk about velocities and accelerations and higher analogs. In some sense, there things are simpler because we don't have to take any limits. We just have a change in position divided by a change in time. So if we're in a very simple situation where we have some unit time trajectory, so for example, let's say we're marching along the Casteljau Bezier polygon of a dCB curve. Okay, so imagine we're just making a discrete walk. Start at P0 at time 0, time 1 you're over here, at time 2 you're over here, at time 3 you're over here, at time 4 you're over here. Now, on the face of it, you might say, well, that has very little to do with the trajectory of the actual curve that we're interested in. But it does have something to do with it because, of course, the polygon is somehow intimately connected with the curve. And so we're going to be interested in relating these two things a little bit more clearly, getting to understand, the relationship more deeply between the polygon, which is this discrete object, and the Casteljau Bezier curve, which is this continuous or analog object. Okay, so if we're in this then discrete time thing, then okay, and here's our quartic. Let's stick to the quartic. So here's our gamma of t. Okay, and here is the expression of the curve in terms of time, a continuous sort of time parameter we can think about. Okay, but now let's consider this discrete uniform motion, as I had said, as we're going around the dCB polygon, say at unit time intervals. Okay, so this is a much simpler story. We don't have to talk about instantaneous velocity or acceleration. We just have differences in position divided by differences in time. And if we're going at unit time intervals, then the change in time is always 1. Okay, so then the change in position is velocity. So that's what the velocity is in this discrete setting. It's just the change in position from one time to the next time. And then correspondingly, the change in velocity is acceleration. Okay, so at every point, it's going to be a velocity, and then we can look at adjacent velocities and take the differences, and then we get acceleration. Now, in physics, you keep going sometimes. Okay, so it's useful to ask, well, what about the change in acceleration? The physicists have a word for that. It's jerk. Okay, so the jerk is the change in acceleration. That's viable both in the discrete and in the analog situation. In the continuous case, it would be like the rate of change of acceleration is jerk. And what about the rate of change of jerk? Well, that's sometimes called snap. but also sometimes the term jounce is used. But snap is more fun because that then motivates the next two in the sequence. Okay, the next two in the sequence, so the rate of change of snap is crackle, and the rate of change of crackle is pop. Okay, that's all very amusing, especially if you like your breakfast cereals. So we have position, velocity, acceleration, jerk, snap, and then crackle and pop a little bit further down the road. But for us, with this quartic situation, we're only going to go up to snap. So let's actually have a look to see what these things look like. All right, so we're going just around the Casteljau Bezier polygon at unit time interval. Okay, so the first, or zeroth velocity, is the position 1 minus position 0, p1 minus p0. And we recognize that's a velocity because it's a difference between points. And then the next one, which we could call v1, would be p2 minus p1. Okay, so note that this p1 minus p0 is already appearing. It's appearing right here in our expression of our curve, of our actual Casteljau Bezier curve, when expressed in this form where we're expanding in powers of t. Okay, so yes, this velocity already has a realization in the mathematics of the curve. Okay, now what is the acceleration? Well, the acceleration is the rate of change of the velocity, or the difference of velocity in this case, because it's just a discrete thing. So it's v1 minus v0. Okay, so if we take this velocity, we subtract this velocity, then we get p2 minus 2p1 plus p0. And okay, I should change my notation. Yeah, I think to be a little bit consistent, maybe I should go in increasing indices. So let me do that actually. It's just a matter of convention. Let's just change this. Okay, so that's the acceleration. And okay, you could call this different things, but I'm going to call this A0. Okay, it's sort of like our first acceleration, but our first is the zeroth one. Okay, so then the change in acceleration is jerk. Okay, so what's the zeroth jerk going to be? Well, it's going to be the A1 acceleration, which is what you get when you take this expression, you just jack up all the indices by 1. Okay, so it will be, this one, A1 would be P1 minus 2P2 plus P3. And then when you subtract A0, which is this one, you're going to get this expression. Okay, and I'm going to rewrite this actually. Let me rewrite it as, just to put it in sort of increasing order. So I have to change the sign. 1, 2, I guess that one has a minus sign, and then plus P3. Does that look about right? Yeah, I think that's right. Okay, so we'll use that instead. So that is J0, the zeroth jerk. Okay, and that's the same thing as this thing here. We'll just put it in there. Okay, then what about snap? Well, snap is the change in jerk. So it's J1 minus J0. So we take this expression here and bump up all the indices. That'll give us J1, and subtract J0, which is what we have here. Okay, so please check that you take this thing here, you bump up all the indices, and then you subtract what you have here. Then you're getting this expression. And I'm going to allow myself to just rewrite that. In this case, it's symmetrical, so it's easier to change to get sort of forward order. 4, okay? And that's exactly what's appearing here. So, and we see these are just the vector quantities that appear in the formula for gamma of t. That's, I think, a really nice observation, and a very important observation. Okay, that there's something physical about these things that are appearing here. These vectors that are appearing are not just random things. Okay, they are just a record of the velocity, the acceleration, the jerk, and the snap at the starting point. Now, since the sum of coefficients of all of these are 0, they're all vector quantities, as we see. These are all vector quantities. So in this expression here, there's only one point. There's a point P0, and then we have these vector quantities that are, of course, multiplied also by these, first of all, binomial coefficients, 4, 6, 4, 1, and also increasing powers of t. So we'd like to understand these vectors which are appearing here, like geometrically, in our diagram, if we went up to here, where are these vectors appearing? Well, the zeroth, or the vector velocity is easy. That's just the vector from P0 to P1. So that's that vector there. Okay, fine. But what about the other vectors? How can we realize them on the diagram? Okay, so a way of doing that is to rewrite these formulas and re-express them as differences of points. Okay, once we take one of these expressions and write it as one point minus another point, then we immediately have a physical interpretation of it, because then the vector is the vector from the tail point to the head point. Then we can see that vector on our diagram. Okay, now there's no unique way of doing this, so you can manipulate these things in quite a wide variety of ways. But I'm going to do it in a way which is maybe sort of naive. Okay, so let's have a look at what I'm doing here. See, I'm not trying to do anything clever. I'm just sort of looking at this thing carefully, and I want to be systematic, and I want to be like an accountant. Okay, I don't want to be like a genius. I want to be like an accountant, just balancing the books, recording what the assets are, being careful that I'm writing things down clearly. It's a good attitude to have. Okay, we're aiming to be careful observers and recorders of what's happening here. Okay, so. Right, what are we doing? So V0 is already very nice the way it is. We understand its geometrical significance. Okay, what about this A0? Well, it's easier if, this is a vector. Okay, this is a vector. It's easier if I multiply it by a half. Okay, if I multiply it by half, then I get a coefficient of a half here and a half here, and I get a minus P1. Okay, I like the minus P1 because that's then minus a point. And the 1/2 P0 plus 1/2 P2, that thing there, we recognize that's actually a point also. Okay, so if I label this point E, which is just the midpoint of P0 and P2, okay, then I can see that what we have here is E minus P1, telling us that this is a vector from P1 to E, from the P1 point to the midpoint of P0 and P2. I'm going to show you what that looks like in a second. Let's just have a look at the next one, the jerk, J0. Okay, so again, I want to write this as a difference of points. And to make that easier, I'm going to divide everything by 4. So let's look at 1/4 of this. Okay, so if I divide by a quarter, then I'm going to get coefficients of like 1/4 here and here, and 3/4 here and here. Now what I'm going to do is I'm just going to take the terms with positive coefficients, the 3P1 and the P3, and put them together. Okay, and the ones with the negative coefficients and put them together. Then I have point minus point. Okay, so once I've divided by 4 and brought the 3P1 and the P3 together, I get 3/4 P1 plus 1/4 P3. And I put a little bracket around that, and I can think of that now as a point because it's an affine combination, sum of coefficients is 1. And what's left over is minus 1/4 P0 plus 3/4 P2. And I can think of that as a point because it's a sum with coefficients summing to 1. And I can call this point D, say, and this point C, say. And so now I've expressed 1/4, the jerk J0, as a difference D minus C. Okay, let me show you now before I get to the snap. Let's have a look here. Let's just okay, here we can see. So the 1/2 of the acceleration, that's E minus P1. Okay, where is E? Here is E. That's the midpoint between P0 and P2. Right? That's the midpoint E, and P1 is here. All right, and so you can see that the acceleration, well, half of the acceleration is the vector from P1 to E. So the full acceleration would be twice that. And notice that in this case here, it appears to go through R0. Maybe it even looks like R0 is the midpoint there. And so that's something that we could easily check. You could easily check whether that's actually the case or not, or just is a happy accident. Please do that. Okay, what about the jerk? So 1/4 times the jerk is D minus C. And what is D? D is a combination of P1 and P3. So here's P1, okay, and here's P3. So this first point, D, is somewhere on here. And where is it? Well, it's obtained by having a weighting of 3/4 of P1 and 1/4 of P3. So there it is right there. There's D, okay? And it's obtained by taking the midpoint of P1 and P3 and taking the midpoint of that and P1. So this is like in the ratio of 1 to 3. Representing the weighting of 3/4 and 1/4. So that's that point D there. That's the head of this vector. And the tail is at this point C, which is 1/4 P0 plus 3/4 of P2. So we're doing the same kind of thing along this dotted line from P0 to P2. We're going up to this point C, which is right here. So we go halfway, so there's a midpoint somewhere. Maybe it's over here. Or maybe not. And then we take the midpoint between that and P2 to get this point C. Okay, so this is in the ratio of 1 to 3 along this line here. So we've got the head and the tail. There's the head, there's the tail. All right, so this jerk vector, or at least 1/4 of the jerk vector, is this vector from this point to this point. Great. Okay, and now the last expression is the snap. So over here we saw the snap is the differences in jerks, and this is the expression that we have for it. And there's 3 positive terms: the P0, the P2, and the P4 term. So we can bring them together. Okay, we'll have to divide by 8 to make things convenient. Then we get 1/8 P0 plus 6/8 of P2 plus 1/8 of P4. So that's in total of sum of 1. So that's actually a point. Let's call it A. And the negative terms are 4P1 minus 4P3. When we divide by 8, we get minus 1/2 P1. What's happening here? There should be a half there. Plus 1/2 P3. So we see that's the midpoint between P1 and P3. All right, so this is A, this is B. Let's see where these things are on the diagram. Where's A? Here's A. Where is this thing here? So this is a combination of P0. Here's P0. P2. There's P2. And there's P4. So one way of thinking about what this thing is actually 3/4 of P2 plus 1/4 of the midpoint of P0 and P4. So you could rewrite these two terms here. If you take 1/2 of P0 plus 1/2 of P4, you're getting the affine point, which is the midpoint of them. I'm calling it M down here. Okay, so again, you could rewrite this a little bit further and then you can see that this point here, this first point A, is 1/4 m plus 3/4 of p2. So it's also the same kind of construction. We start with m now and go up to p2. We go halfway and then halfway, halfway. So that's the point A, 3/4 of the way along between m and p2. And the point B, well, that's just the midpoint of P1 and P3, which is this point down here. That's B. So the 1/8 of the snap is this vector here. Okay, so let's just scroll down here, admire this. So we have our Casteljau Bezier polygon here, which is these 5 points. But now associated to those are these vectors, okay, which are intrinsically associated with the curve. These are these coefficients of ascending powers of t, aside from the binomial coefficients. And these vectors have this now geometrical interpretation that there's the velocity vector p1 minus p0. This thing here, or half of it, is that's that one there. That's like the acceleration. And this thing here, the jerk, that one was this thing here, from this C to this D. And this thing here, the snap, okay, this is actually 1/8 of that, is from here to here. So you see there's a lot more to this Casteljau Bezier polygon that meets the eye. Okay, there's these sort of secondary things which are not immediately visible, okay, which requires some, okay, it's relatively simple, some simple algebra. I mean, a primary school student could kind of follow this reasoning, but it's a little bit surprising where all these points are. It's a little bit rich. And we're going to see in our next video that this is all intimately connected with very classical calculus, going back to Gregory Newton and earlier even to Thomas Harriot, where the difference calculus first comes into view.